So I found myself wondering the other day, I said, what's better than a problem with one derivative rule? And I came to the exciting conclusion that the only thing better than a problem with one derivative rule is a problem with two derivative rules. So that's what we're going to look at here in this section. We're going to look at problems that involve multiple derivative rules, because at this point now we have the chain rule, the product rule, and the quotient rule. And utilizing them all simultaneously and deciding which one to use, I think, can be one of the most difficult parts of taking derivatives. Just figuring out what derivative rule do I need to use, or okay, if I have a product rule and a chain rule together, what does that look like? So hopefully we'll take a look at plenty of examples to so that we can feel a little bit more confident about using multiple derivative rules. So let's hop right in. I've got y equals t squared divided by t plus 1 all to the negative third power. And I think there's definitely some hints that you can look for when determining what derivative rules you're going to use. First of all, I see t squared over t plus 1. I see that rational function, anything that kind of looks like a fraction. To me, this looks like a quotient rule, for sure. So I'm going to label what we're doing here. We've got a quotient rule. The other thing, this isn't quite as hard and fast of a rule. We said earlier, you know what, if you have parentheses, it's kind of a really big hint to using the chain rule. And that's not always the case. However, I'll say most of the time, many times it is. So in this case, it is actually the case that we're going to need to use the chain rule, because what we're really looking for is a function. So we have t squared divided by t plus 1 inside of another function. Inside of this function, u to the negative 3 or x to the negative 3. So if we have more than one derivative rule, we said this is a quotient and a chain rule. I like to really kind of break this down and take my time with these. So I will kind of go back to the fundamentals of taking derivatives. I'll fall back on, writing out the formula for the product rule or the 4 steps for the chain rule, things like that. I think those are just going to be helpful for us. And some of these you can kind of look at, and I've always viewed them as having one derivative rule inside of another derivative rule. So I look at this, I see a quotient rule inside of a chain rule. So I see a quotient rule inside of a chain rule. You can actually say quotient inside of chain if you need to. I think I'm going to start with the chain rule here. I think that kind of makes the most sense. I'm going to start with the chain rule. I'm going to pick that inner function. So when we work with the chain rule, that inner function, that is u equals t squared divided by t plus 1. That's what's inside of my parentheses. And before I even start to find u prime, because I know that's something else that I need to do, let's actually make our substitution. Let's actually plug in u to make sure that we've kind of made the right choice here. So over here we have y equals u to the negative 3 power, kind of looking ahead into the next step at this point. This is something that we know how to take the derivative of. We can just use our power rule. So this is good. Alright, so we have u. We kind of skipped over finding u prime, so let's go ahead and do that right now. U prime, here is where the quotient rule is going to come into play, because I'm going to need the quotient rule in order to take the derivative of u. So the derivative of, quotient rule low, so that would be t plus 1. D high, derivative of t squared, that's going to be 2t, minus high, that's t squared. D low, derivative of my denominator in this case would just be 1, divided by t plus 1 quantity squared. So we can simplify this a little bit. Let's distribute 2t. I've got 2t squared plus 2t minus t squared all over t plus 1 quantity squared. This would be t squared plus 2t divided by t plus 1 quantity squared. We could factor a little bit more, to be honest, but I don't think it's worth it. So this is my u prime. So at this point, we've done the quotient rule. That part is, we're done with the quotient rule. Now we're just focused in on chain. All right, so what would our next step be? We kind of jumped ahead here. We wanted to rewrite this, take out our u. We took out t squared divided by t plus 1, this guy right here, and replaced it with u. So we should have u to the negative 3 power, which is good. So my third step, I'm going to take the derivative of this. So y prime is negative 3 times u to the negative 4th power. But we're using the chain rule here, so we need to remember to multiply by that u prime. So my fourth step then, y prime is equal to negative 3 times u. Well, what is u? U is t squared divided by t plus 1 to the negative 4th power times u prime. That's going to be t squared plus 2t divided by t plus 1 quantity squared. To be fair, we absolutely could simplify this a little bit. I see a little bit that could go on here, but I think this is a good place to stop. When we have more than one derivative rule, I might tweak a few things at the end. I might multiply a couple monomials or something like that. But generally, these problems are difficult enough to the point where I'll say, okay, if you can get it to this stage right here and not really worry about simplifying it, that's what I want to see. Because that's you, as you have then shown me at this point that you know how to use the quotient rule and the chain rule. And that's really what I'm interested in. The rest after that, that's just algebra. I'm not too worried about that. I'm worried about, can you use the quotient rule and the chain rule together in one single problem. So let's look at our next example. Let's change up our color. Let's do this in red. Here I have y equals e to the negative 4x power divided by x squared plus 1. Well, shoot, I look at this, I see that fraction. I see that, well, it's not quite a rational, but I see something that looks similar to a rational function. Definitely say, okay, there's going to be a quotient rule in here for sure. And then, at this point, you might not notice anything kind of offhand. You might say, well, there's nothing that really jumps out at me as like a chain rule or a product rule or anything like that. So in this case, I'm just going to look at, well, what does the numerator and the denominator look like? I know I'm going to need to take the derivative of both of those inside of my quotient rule. So let's just look at these. E to the negative 4x. Do I know what the derivative of that is, kind of like, you know, right off the top of my head, or do I need to use a derivative rule? If this was e to the x, I could deal with it, but e to the negative 4x, no, this is where the chain rule is happening. I'm going to need the chain rule for that part right here. So this is a quotient and a chain rule, once again. I think kind of the big difference between this problem and the last problem, because they both had a quotient and a chain rule. When I look at this problem, I see a quotient rule inside of a chain rule. Here I think this is sort of reversed. I see a chain rule inside of a quotient rule. So it's up to you to decide how you want to start. I think I'm going to do the chain rule. This is a pretty small chain rule. I think I'm going to do this off to the side over here. So my chain rule, let's just look at that derivative, or excuse me, that numerator for a moment here. I'm just going to look at y equals e to the negative 4x power. Let's just focus on that. So I need to find u and u prime. That's my first step. So u, that's going to be my power right here. That's going to be negative 4x. U prime, the derivative, would just be negative 4. So when I make my substitution, oops, this is step 1. Step 2, I'm going to make my substitution. So y equals e to the u power. so that I can take my derivative, step 3, I can take my derivative y prime, derivative of e to the u, that's just e to the u times u prime. And then in step 4, we're going to go ahead and plug in our u and our u prime. So y prime is equal to e to the negative 4x times u prime, that's negative 4. I'm just going to rewrite this just to make it look a little bit nicer. Negative 4e to the negative 4x power. So that's just the derivative of the numerator. So now I got to come back and look at the quotient rule, because at this point I'm done with the chain rule. That was all that work I just did on the right-hand side. So okay, let's talk about the quotient rule here. Quotient rule. Let's see. Quotient rule says low, that's x squared plus 1. D high, derivative of my numerator. So I want the derivative of e to the negative 4x. And this is the point where I would need to use the chain rule. But lucky for us, I already found the derivative of my numerator. We said that was negative 4 times e to the negative 4x. And this is why I kind of like to try and split up my derivative rules as much as I possibly can, because otherwise we're trying to kind of juggle 2 derivative rules at the same time. You've got to like stop one and start the other and kind of just remember where we are. We're jumping around like crazy. I think this is really nice because now it's much more obvious to me that I've already done the work for the chain rule. That's all over here. So now I'm just focused on quotient rule. And when it comes time to say d high, derivative of my numerator, I can just say, you know what, I did that work. It's right here. Just plug it in. So low d high, derivative of my numerator would be negative 4e to the negative 4x minus high, that's e to the negative 4x. D low, derivative of my denominator will be, let's see, just 2x. Divided by x squared plus 1 quantity squared. That's the most important part. If you can get to this step, this is what I want to see. This is the derivative. If you really wanted to simplify, I probably would just a little bit here. I see a common factor of e to the negative 4x. I would factor that out just because it's not too terribly difficult to do. E to the negative 4x. So I factored e to the negative 4x. I factored this part out. Over here I'm going to distribute negative 4. So this would be negative 4x squared minus 4. Then we've got minus 2x. All divided by x squared plus 1 quantity squared. And yeah, sure, we could factor out a negative, we could write it in standard form, we could do all this stuff, but I think that this is probably as far as I would push this problem. So you know what? There's my derivative. All right, so let's look at a couple more here. I think we've got 2 more. Next, I've got y equals e to the x times the square root of x squared plus 4x plus 5. All right, so this one, let's see. I got to figure out what derivative rules I've got. And I would almost encourage you to read these out loud to yourself and say exactly what you're doing. So this is e, yes, it's e to the x square root of x squared plus 4x plus 5. But what am I doing between these two things when they're right next to each other like that? Right? This really says e to the x times square root of x squared plus 4x plus 5. As soon as you say that times, that kind of makes me think, oh yeah, product rule. That was one that we learned. So this is a product rule for sure. Again, just like last time, I would also look at the parts of the product rule. E to the x. Well, I know the derivative of e to the x. That's just e to the x. Square root of x squared plus 4x plus 5. Hold on a second there. This guy. That's going to be a chain rule. So let's see, how do I want to do this? And for the record here, I see a chain rule inside of the whole product rule if you're kind of taking that approach if you're thinking about these derivative rules, almost as being nested, having one derivative rule inside of another. So let's see, what should we start with here? I think I'm going to start with the... Well, actually, first of all, let's rewrite this. E to the x, this is going to be x squared plus 4x plus 5 all to the 1/2 power. And if you didn't see the chain rule before, hopefully you do now. So I'm going to rewrite it first of all. I'll call this f, I'll call this g. And let's see, for a product rule, I know I need f prime times g plus f times g prime. So I'm going to do some scratch work over here. Let's say, okay, f is equal to e to the x. I know I need f prime as well, so f prime is also e to the x. G, that's x squared plus 4x plus 5 to the 1/2 power. G prime is 1/2 times, well, I'm jumping the gun here. G prime, now is what I'm going to have to use the chain rule. So it's up to you. If you feel comfortable enough to take the derivative right here, right now with the chain rule, you can. Otherwise, maybe just make yourself a little bit of room down here. And let's do that. Let's say g is equal to x squared plus 4x plus 5 to the 1/2 power. So u is that inside part, x squared plus 4x plus 5. U prime is equal to 2x plus 4. So g is really equal to x, oops, nope, I'm taking out x. So this is actually just u to the 1/2. G prime then, 1/2, inside part stays the same, subtract 1 times u prime. So I would have 1/2 times u, that's x squared plus 4x plus 5 to the negative 1/2 power. We'll worry about that negative power later. Times 2x plus 4. And sure, again, we could simplify this. I see, hey, you could factor out a 2 and cancel that 1/2 if you really wanted to, but I don't want to worry about algebra yet. So this is my g prime. So I'm going to say, okay, over here, g prime, that's actually just 1/2 times x squared plus 4x plus 5 to the negative 1/2 times 2x plus 4. I shouldn't say just that. It's a pretty long derivative. So now I'm going to come back to my product rule. I said, okay, this is what I'm looking for my product rule. F prime times g plus f times g prime. So let's just plug in what we know, f prime. So let's say y prime is f prime, that's e to the x times g. This is x squared plus 4x plus 5 to the 1/2 power plus f, that's e to the x, times g prime. Here's 1/2 times x squared plus 4x plus 5 to the negative 1/2 power. I'm running out of room, so I am going to have to do some erasing right here. Let's see, let's get rid of some of this stuff here. There we go. 1/2 x squared plus 4x plus 5 to the negative 1/2 times 2x plus 4. And again, there's all sorts of stuff you could do to simplify this. Like, for example, I see a factor of e to the x here that we could factor out if we really wanted to. I'll show just a little bit of simplifying here. E to the x, that would leave me with x squared plus 4x plus 5 to the 1/2 power. I'm also going to do one quick thing with this guy right here. I'm going to rewrite 2x plus 4 as 2 times x plus 2 so that I can go ahead and cancel this guy and this guy. So let's see, what would that leave me with? That would leave me with plus x squared plus 4x plus 5 to the negative 1/2 power times x plus 2. That's probably above what I would expect most of you to simplify to. If you don't simplify to that step, then that's okay. Because as I'm looking at it, I'm like, boy, that looks complicated. You could even go further, though, if you really wanted to. You could find a common denominator between this guy, because this really belongs in the denominator of a fraction. You'd find a common denominator between this and this function over here if you really, really wanted to. But I think that's a good place to stop for that example. Let's look at one more. I think this one's kind of sneaky. So it's a good one to end on, I think. Here I've got y equals cotangent of e to the 3x. So y equals cotangent e to the 3x. And as I'm looking at this, I'm going to change this just a little bit because this isn't quite what I want it to be. Let's alter it because this problem actually, as I'm looking at, I think it's too easy. Is it? No. I'm sorry. I'm second guessing myself. This is good. All right. As I look at this, I'm going to see, first of all, this e to the 3x. And hopefully you're starting to see a pattern where anytime we have anything more complicated than just x in our power for an exponential, so if I have e to the x squared or e to the 3x here in this case, that's going to be a chain rule. So this is definitely a chain rule. And what I have here also, this is a very subtle one, I think. I don't have a quotient rule. I think that one's pretty clear. Don't really have a product rule because I'm not multiplying these two things. A common mistake is I'll see people say cotangent times e to the 3x, but that's not at all what we're doing. This is cotangent of e to the 3x. This one's kind of very subtle, and so it's kind of a simple case of actually a chain rule and a chain rule. And I'll show you why that is here. So let's just look at this part first. Let's say I'm working with y equals e to the 3x power. If I'm working with this guy, I'm going to say, okay, well, I should pick u. I should pick u equals to 3x, right? That would be my power, or excuse me, my inside part. U prime then is just 3. So, okay, I know that when I make my substitution, this is really y equals e to the u. So when I take my derivative, this is really going to be e to the u times u prime. So my fourth step then, let's take u and u prime, we'll plug those back in. Y prime is equal to e to the 3x times 3. And let's go ahead and rewrite those. That's really 3 times e to the 3x power. But that's just the derivative of this inside part right here. That's not actually what I want, because really what I have here, I've looked at the derivative of the inside part without actually going and looking at the outside part right here, this cotangent function. So I might say, okay, I actually have a second chain rule. I have this e to the 3x that's inside of this cotangent function. If you're having trouble seeing this chain rule inside of the chain rule, I have 3x inside of the exponential e to the x, which is inside of cotangent of x. So, all right. I don't necessarily want to use u because maybe you say I've already used u. I don't really want to use u again. Need like a second u so that I don't get confused. Maybe like maybe like a w perhaps. That was a terrible joke, I'm sorry, but not that sorry. All right, so W, I'm going to pick to be this inside part. Now, W is going to be e to the 3x, and W prime is the derivative of e to the 3x, but we actually did that. We said if we're working with e to the 3x, that the derivative is 3e to the 3x. So we've done that first chain rule already. So W prime, that's really 3e to the 3x. If I go over here and I make my substitution now, y is equal to cotangent of W. So y prime, I know how to take the derivative of cotangent, oh boy, I'm blanking, derivative of tangent is secant squared, so derivative of cotangent is opposite cosecant squared W. But we're doing a chain rule here, so we need to multiply by W prime. All right, so now we just need to take our W and our W prime and plug those into our derivative. So let's do that. Y prime is equal to negative cosecant squared of W, that's really e to the 3x, times W prime 3e to the 3x. You could leave your answer like this. I will say I think that this guy being here at the end, this exponential function, is perhaps a little bit jarring to see because normally we say cosecant squared of e to the 3x, and then it might be confusing to see that 3e to the 3x there as well. It's really easy, I think, to make an order of operations mistake there. So I would just bump this guy up to the front. I would say that this is really negative 3e to the 3x times cosecant squared of e to the 3x. Here is my derivative. So this one is by far, I think, kind of the trickiest to see, and hopefully we'll have an opportunity in some later videos to look at some more double chain rule problems. I'm sure that there are at least one or two in the homework, so I would definitely recommend looking at those because I think that these are the trickiest to spot of all of the kind of derivative rule combinations that we have is a chain rule inside of a chain rule. And part of that is just because a chain rule is so new. So hopefully as we develop more practice with the chain rule, we'll start to feel a little bit more comfortable, and we'll feel more confident in identifying when we have a double chain rule for a derivative.